And the second one is the second norm over the weight Q. Okay, I'm expecting you to tell me what it is. And the reason that I'm expecting you to tell me what it is, because we had the formula in your notes. So let's try it together, huh? What was norm 2 of x?
Square root.
Yeah, but in the vector form it is
X transpose.
the inner product of x, right? Or 1 over 2. Or 1 over 2. So if I have the norm x2 of weight q, it is like the inner product, the weighted inner product, right? The weighted inner product. How can I calculate this one? How can I calculate this one? It was on Friday lecture. It is x Hermitian q x, right? This is the weighted inner product to power 1 over 2. And there was something about this q. What was the condition over the q?
It should be n by n.
It should be Hermitian. And it should be positive. Now, in many books, in many papers, you may see that norm to Q is written as norm Q, because usually we do not write 2. Like norm 2, we just, if we put the sign of norm, it means that norm 2. Now we want to talk about two very well-known inequalities in norms. The first one is Holder inequality. Which says let x and y belongs to Cn, then the magnitude of inner product of x and y, which is the magnitude of x Hermitian y, is less than or equal to norm, the p norm of x plus the q norm of y, where 1 over p plus 1 over q is equal to 1. So for any p and q which are satisfying this condition, we have such an inequality. We can, the inner product of x and y is always less than the norm of x plus the norm of y. In case of p is equal to q is equal to 2, we have the triangle inequality. And the next inequality is called Cauchy-Bunyakovsky Schwarz inequality. And it says that let x and y again be in the Cn. Then the inner product of x and y, which is the magnitude of x h y, is less than or equal to norm of x multiplied by norm of y. And by norm we mean the Euclidean norm. Here, the equality happens if and only if x and y are linearly dependent. Note that the angle theta between any two non-zero vector of x and y belonging to Cn is cosine theta is the magnitude of x Hermitian y divided by norm x multiplied by norm y. Another note is the second norm is unitary invariant, where, however, norm 1 and norm infinity are not unitary invariant. In other words, if U belongs to C n by n is unitary, then the norm of ux, norm 2 of ux is equal to norm of x, because And of course, in order to prove it, you should remember what is unitary. What is unitary?
U Hermitian to be equal to U, right? Or
U Hermitian.
no?
No, we don't call it unitary, we call it Hermitian. U Hermitian equal to U, like Q Hermitian equal to Q, we said it's called unitary, like Q transpose is equal to Q, which you said that's symmetric. How do we prove it? By definition, right? Norm of Ux is X Hermitian, U Hermitian multiplied by U H, sorry, Ux. Now, because U is unitary, this is I, so this is x to the power 1 over 2, is X Hermitian x to the power 1 over 2, which is norm of X. Obviously, norm 1 or norm of infinity are not unitary, invariant. Like if you multiply them by U, you are changing the results. If X and Y belongs to Cn are orthogonal. What does it mean? X and Y are orthogonal? Let's say X and Y are orthogonal.
And the product is 0.
Inner product is 0. Very good. Then we have Pythagorean identity, which means the norm of x plus y, or plus minus y, square is equal to the norm of x square plus norm of y square. So if x and y are perpendicular to each other, if x and y are perpendicular to each other, we have the Pythagorean theorem, right? This right angle triangle, right? Three more notes. Norm 1 of x is less than or equal to square root of n norm x2. Norm 1 of x is less than or equal to n multiplied by norm x infinity. Norm of x is less than or equal to s square root of n norm infinity. There are three norms also. In general, norm 2 is less than or equal to norm 1. norm infinity is less than or equal to norm 1. And again, norm infinity is less than or equal to norm 2. And it's kind of, especially the last three, is kind of obvious in the sense that norm infinity will give you only one of the elements. Norm infinity will give you one of the elements, which is the biggest element. But norm 1, for instance, will give you the addition of all the elements. In other words, the biggest element will be added by some other positive numbers. So obviously norm 1 is bigger. Norm 2, again, we can have a feeling that it will be less than the norm 1. But if it has two elements, easily by triangle inequality can be proved. So, yeah.
So then the infinity norm is the least norms of all norms, or?
Yeah, it's so small because it only gives you one of the elements. The other ones give you some kind of addition of the elements. Like in norm 1, you have the addition of all the elements. One of these elements, only one of them is norm infinity. Norm infinity will tell you that, okay, I'm looking at all your elements and only pick up one. Whereas the other one says that I'm adding all the elements. So it's obvious that you are adding something to your biggest value, so it's increase.
And this holds true for all?
Yeah, always. Okay. Always. Now, what we have done till now, we were talking about the vectors, right? And the course is about mainly matrices. So we have to start to talk about a matrix norm. So all type of norms that we have till now, all type of theorems that we had now, we have to discuss about them in the matrix form. Then we have to talk about norm 1 of the matrix, norm infinity of the matrix, p norm of the matrix, and so on. Which we will do it on Friday. Do you have any question? If you have no question, this is the end of the lecture for today. You may stop the video.